We are going to be talking about rotational motion. Remember, there is a difference between rotating and revolving, and both belong to circular motion. We are going to look at today the rotation portion of motion. And when we discuss rotational motion, we do need to make it clear that Newton's first law, which is also known as the law of inertia for linear movement, is also the same for rotating objects. All rotating objects will continue to rotate, or non-rotating objects will continue not to rotate unless they are acted by an outside force, something that will stop it from doing whatever it wants to do originally. Which brings us to rotational inertia, also known as moment of inertia. This is the resistance of an object to change its rotational motion. The higher an object's rotational inertia, the more difficult it will be to change its rotational speed. In order to change the object's rotational speed or state of motion, we need something called torque. Torque must be applied. What is torque? Torque is pretty much a force that turns objects. It's a turning force. It produces rotational acceleration. It's different from a force because a force causes linear acceleration, and torque is specifically to cause rotation, so circular motion. Here are some examples. So you see using a doorknob or using the top part of the faucet and turning it, and then also putting leverage on a wrench, so pulling the wrench from side to side, which would create torque. Leverage is how torque is produced. The longer the handle, the greater the leverage, and the easier it is to accelerate rotation. For example, you'll notice there are 3 wrenches shown below. One is short, one is a little longer, and one is very long. The longer that you have the handle and your hand is on the end, the more force that you can actually give, the more force, the more torque that you would have. One example is when you open a door. It is not the turning of the knob, but it is actually the perpendicular force that you push the door open, because the rotation is occurring here on the hinge. So when you apply a force, with the force being furthest away, so here's your lever arm, the further away that your doorknob is and your push is perpendicular, then you are going to be able to easily open the door and cause the rotation to occur here at the hinge. If you were to have this doorknob closer to the hinge, it would require more force to do the same work that you would need if you just put the doorknob and the push here. So, here's a question. If you cannot exert enough torque to turn a stubborn bolt, would more torque be produced if you fastened a length of rope to the wrench handle as shown below? So here is a picture of a girl who has decided to put a rope on the end of this lever. And she's trying to get this to turn because she couldn't get it with just her hands. What do you think? The answer is no. You would not be producing more torque because the lever arm is exactly the same length or the same height. To increase the lever arm, it would be better to use a pipe and put the pipe on the top up here and then pull from up top above the pipe. That would give you more leverage, that would create more torque, and that could possibly give you enough energy in order, or enough force to pull that bolt and make it loose. Rotational inertia and mass. So there is a relationship, and it depends on where the mass is located in relation to the axis of rotation. The greater the distance between an object's mass concentration and the axis of rotation, the greater the rotational inertia. So if you look at this picture down here, what you will notice is that we have a rod that has two masses on it, and the hand is right here, and this is where the axis of rotation is. The weights are closer together towards the center, which is the axis of rotation. It is easy to rotate this object. If I were to move the weights or the masses away from the center, also known as the axis of rotation, it would be difficult, more difficult, to rotate the same masses. Here's an example of a person who is holding a long pole, and he is walking across this tightrope. Without this stick, it would be more difficult to walk across. It becomes easier when he has this rod that goes across his body because his center of axis or his axis of rotation would be in the center of his body. Because he now has a rod which has mass that is outside of his axis of rotation, this creates less movement, so he's more steady. Another example is depending on where you hold a baseball bat, it could be easier to swing or more difficult to swing. So it depends on where your hands are, which creates where the axis of rotation is. Here, on the upper bat, we have our hands further up on the bat. This creates the mass is closer to the center of your axis, the axis of rotation. Because the mass is closer to your axis of rotation, you have less rotational inertia, which means it's easier to twirl. You need less force in order to swing the bat. The further away from the mass, so here is my axis of rotation, and most of the mass is up here on the other end. It is going to take more force in order to move this bat. Because it takes more force, we say that it has more rotational inertia. Another example, and you don't have to write this down unless you want to, these are great examples. The axis of rotation is where it is hinged up at the top, so where it is connected at the top. Notice that the length, the masses are down here, and it is a certain distance away from the axis of rotation. Versus over here, we have a pendulum whose masses are hanging much further away. Remember that if you're closer to the axis of rotation, you will have a larger amount of speed. So the shorter pendulum swings faster than that of the longer. This also is true for animals. The length of your legs, because this dog's center or his axis of rotation is up here, his legs are further away, this dog here is going to experience a harder time to move as quickly as this little dog over here with shorter legs. So short legs equal less rotational inertia, and it's easier to move. For humans, this is also true. However, we can change things up. For example, if you were to bend your legs when you run, it would reduce your rotational inertia because it puts the mass of your legs closer to your center of gravity, which is your rotation, your axis of rotation. By bending your legs, it's actually easier to swing back and forth. Pretty cool. All right, so on to the formula for inertia. When all the mass, and this is specifically for only when the mass of an object is concentrated at the same distance, radius r, from a rotational axis, the rotational inertia is mass times radius squared. And rotational inertia is denoted as a big letter I. You do not need to write this down, but I just wanted to show you that rotational inertias are very different depending on the shape and size and the axis of the object that you're looking at. We have learned this one right here. Rotational inertia equals mass times radius squared. Also over here. So these two are similar. However, Depending on if you take into account the diameter, it changes, or whether or not your mass is long, then it would also change. So this is just to give you an idea that there are different equations depending on the shape and the axis of the object. Angular momentum. Angular momentum is a vector quantity. It talks about the strength of rotation. How strong is your rotation? When rotational speed has a direction, we call it rotational velocity. Just like speed is a scalar, when we give it direction, it becomes velocity. Angular momentum depends on rotational velocity and inertia. The angular momentum formula is angular momentum equals rotational inertia, which is denoted by I equals mass times radius squared. And this might look familiar to you. This is the rotational velocity denoted by omega. And the equation for this is V equals R omega. Now, one thing to note is that we want to change this and solve for omega. So when we do that, we get omega equals velocity over radius. Now, let's plug this in to here. So we have I equals mr squared, so we have mr squared, and then we have times omega, which is velocity over radius. The radius, or the radii, are going to cancel, leaving us with one radius, and that is going to give us a grand total for angular momentum is now equal to mvr, mass times velocity times radius. And this is, again, how strong the rotation is of the object. There is a law of conservation for angular momentum, and it simply states that if no unbalanced external force acts on a rotating system, the angular momentum is constant. Here is an example of a man in two different positions while standing on a turntable. When the man pulls his arms inward, what he is creating is he's decreasing his rotational inertia. Remember that as you have your mass closer to your axis of rotation, you will have a lower rotational inertia, which means that it's easier to move you, which means that his rotational speed is going to increase. Notice down here how by pulling the mass of the weights inside closer to his center, his rotational inertia is going to be smaller, which means he's easier to move, which makes his rotational velocity greater, so that way he's actually spinning faster than if he were to pull his arms out and take the mass away from his axis of rotation, which would then increase his rotational inertia, which would then mean that he is harder to move. And if he's harder to move, then that would mean his inertia would be greater, or his rotational inertia will be greater, harder to move, and therefore he would have a small rotational velocity. He is not moving as quickly as the second picture. This also leads us to explaining when you see a gymnast who does a flip, and notice that the speed when his knees come closer and he pulls the mass of his legs and his arms closer to the center of his body, he moves faster than when he's about to land and his arms and his legs come out and then he slows down. Pretty cool. So be ready to use this information in class, and we'll see you soon.